Good afternoon and welcome to everybody who is here. This is the Dune research presentations, which are being presented on behalf of the first year Research in Earth Sciences course and program. That's a mouthful, so we abbreviate that as the FIRES program. And about the many people that we need to acknowledge, you're going to be seeing the students who have done the research and hearing about the results of their research. Behind the scenes, who you won't be seeing up on the stage will be their research mentors, who are upper level students in the department who have helped them through with this. But we also are doing a few new things technically this year. And so I just want to acknowledge that we have technical assistance by Isaiah, who's a previous FIRE student and a FIRES mentor, by Jacob, who's the FIRES coordinator for this year. And this probably wouldn't be possible right now without Kelvin's information technology, who discovered ransomware on this room's computer last night and re-imaged the computer this morning, and that process finished about 10 minutes before we started loading stuff up here. So we're excited that we can show you these presentations and not have to move to another room. What we'll be doing this afternoon, we'll be seeing 5 presentations from 5 different research groups. Each presentation will be about 10 to 12 minutes long. There will be time for questions after each presentation, so I'd encourage you to think about questions. We also would welcome any feedback that you have. I'm not sure if I can juggle the microphone. And my feedback form at the same time. I think the students will handle juggling things better than I will this afternoon. So we have these forms out in the hallway. There may be some mentors that may pass them down. There's a QR code on there. You can fill in an online form to give some feedback, or you can just jot it down on the paper form as well. So I'd like to give the time over for the students, and maybe we can pull the first presentation up on the screen, and our first group can come up, and then I'll introduce, well, they will introduce themselves, but so for this first presentation, we're going to start right at the edge of the beach and hear about things that are going on in that zone. And so please welcome our first group of researchers.
Hi, my name is Zach Geikema. Today we'd like to talk to you about beach wrack and its effect on 2 Michigan beaches. So we wanted to start with a definition of what is beach wrack. And it can simply be explained by anything that's washed up on a shoreline that is either anthropogenic or of natural origin. So we can see some human waste, like the trash, and some natural origin might be, here we have large pieces of woody debris. So that is a example of natural debris on a beach. Our research question of this study was, we wanted to see what are the characteristics of wrack on Michigan beaches. The objectives we used to answer that question, we wanted to measure the characteristics of wrack on 2 of the beaches, document the role of woody debris on a beach system, and we also wanted to record evidence of erosion, deposition, any sand transport that was happening in the area around, especially woody debris.
Our study areas for this project was Hoffmaster State Park and Rosie Mound Natural Area. The picture in the top right shows Rosie Mound Natural Area, and the picture in the bottom left, that is Hoffmaster State Park. One thing that we thought was,
Try flipping the switch. I think it's
on now. Okay. So if you didn't hear me, the top right, that's Rosie Mound Natural Area, and the bottom left is Hoffmaster State Park. One thing that we found interesting about these research areas is to get there from the parking lot, you have to walk through the woods on a boardwalk, and it takes you right onto the dunes. So
So for our first objective, which was measuring characteristics of wrack, we really wanted to study how big is the wrack? What can we see with the size, the distance from the water, and the distance from the foredune. So we really wanted to get an exact location as well. So we used a GPS Trimble to get GPS locations exactly. And we mapped those later, as we'll see in a couple minutes. We also used a compass for angle of orientation, and this was especially useful for the large woody debris, as we were able to see what direction it laid in on the beach in correspondence with the beach angle. And then we also documented all of our study with camera with photo documentation. For our second objective, focusing a lot more on woody debris, here we have our team here. We have the GPS Trimble, and that is me right there, recording down some measurements of each piece of woody debris. And then here's another one of our researchers taking a measurement of a large piece of woody debris. And then for our final objective, we wanted to look at sand transport, and we really used a lot of photo documentation for this. And once again, the measurement of the woody debris came into effect a lot in this last objective.
All right, so now on to results. So once again, the first place, we went to two different places, Hoffmaster State Park and Rosie Mountain National Area. We ended up going to Hoffmaster State Park twice to accomplish two different types of measurement. So the first time we went to Hoffmaster State Park and the only time we went to Rosie Mountain National Area, we took points of wrack every 30 meters apart and documented whether or not there was wrack there, and took our measurements at those 30-meter increments. And for our last column, when we went to Hoffmaster State Park again, we only looked at the large woody debris and measured every single piece of large woody debris that was there. So you can see as the times that we went, and then because we did those 30-meter increments, we were able to find out how often there was wrack present at those increments. So for Hoffmaster State Park, we saw about 72% of the time there was wrack present, and at Rosie Mountain National Area, it was 93.3% of the time. So we found that interesting. Then we have our distance from waterline, which we have our minimum, average, and maximum right now here, but we have a graph up there showing the difference in our average distances, showing that Rosie Mountain and Hoffmaster were both very consistent at about 16 meters when it comes to all wrack, but the large woody debris was on average closer to the water line, a couple meters closer. And then the composition, we found that mostly woody debris was present for all of it. And of course, for the final column, everything we measured was large woody debris. Another thing that I should mention is we have another graph at the bottom there showing our distance from the water versus the distance to the foredune. And what you should look at here is how few of the points are less than 10 meters away from the foredune, showing that they're much closer, and most of them are within 10 meters or more than 10 meters away from the water, showing that they're on average much closer to the foredune and on the back half of the beach. All right, so here in this bottom corner, we decided to, as we said earlier with our compass, we looked at the orientation of the wrack. So here we see that the majority of the wrack that we measured was oriented in a north-south direction, followed by our northwest-southeast, and then decreasing further east to west, lastly, northeast-southwest. Now I'd like to bring your attention over to the picture over there. As you can see, this was for our large woody debris at Hoffmaster State Park, where we have the GPS coordinates of every single point of wrack that we measured. Granted, some of them do look like they're in the water. This is a slightly outdated picture, although all of the points were taken while we were there. So that is why some of them look like they are in the water. But an interesting thing to notice is the orientation of the beach is much more northwest to southeast than a vertical north to south. But if you look at the waves themselves, they are oriented much more north-south. Lastly, we of course were looking at some of the effects of the wrack that it has on the beaches. And we were looking at the sand transport in that time. So on this one, you can see that we are actually standing upwind, looking downwind towards this piece of wrack. And you can see the erosion on either sides of it, where some of the sand has been dug out underneath the piece of wrack. And then there on up in that corner, up in that corner, you can see where we are standing downwind on this one. And you can see the shadow dune that is developing behind that piece of large woody debris, proving that there is definitely lots of sand transport happening around all of the wrack.
Okay, and then for our discussion, our study showed that the displacement of the rack line was a lot closer to the water than the woody debris. The rack line had an average of 16 meters from the water, and the woody debris was about 13 meters. One reason for this is the rack line tends to be smaller pieces of rack, so it's more easily moved by the wind and water. And the large rack can also, because of its mass, sink into the sand a little bit, causing more friction, which means it needs a higher velocity wind to move. Another pattern that we found was interesting was a lot of the rack had a north to south orientation. And we thought this was interesting because the beach was in a northwest to southeast direction. So it was opposite of the beach. And then our conclusions, we found that there was a significant amount of wrack on the beaches and woody debris. We found that there was sand transport near and around the woody debris, and that led to the formation of shadow dunes, which can be seen in these pictures. And here are acknowledgements, and please ask any questions if you have.
So we would welcome questions, and we do have a microphone that can move around in the audience just so that other people can hear your question. And also we welcome our people who are on Zoom to hear the questions as well.
What was the most interesting piece of wrack that you found?
So there was one piece that we found that was really interesting, that it was like a piece of a root, and it kind of just had like a bunch of sticks like tangled all around of it, and it changed the way that the sand formed behind the dune. So it's kind of like all in different sections. So I thought that was pretty interesting.
We have a question from the Zoom chat. They ask, do you think that the rack furthest from the waterline corresponds to the most recent high water storm event?
So we actually originally had planned for there to be, well, not planned, but I hoped. We were hopeful of we can't plan weather, but we were hopeful for a rather large storm in order to change what we were seeing. So that's why we went to Hoffmaster State Park twice originally, was to see if there was any change from storm in a short term. But as for a long term, No, we did not really look into that.
Did you notice any dune grass growing on the shadow dunes?
We did notice at the very south end of Hoffmaster State Park, there was one place where the wrack was very close to the foredune, and so I would assume that that's maybe just like suckers starting out from the grass that was already established in the foredune, then grew into the shadow dune. But other than that, we did not notice a pattern of that occurring.
Do you think the wrack getting buried and then like kind of piling up, do you think that will help the foredunes grow bigger?
I think that it will over time. I think right now we saw a very short-term representation of this, but if there's enough wrack in a certain area, it will form the
Do you have any theories as to where these the wrack and the woody pieces have come? Like, have they come from places in the north where trees have like fallen in because of erosion, or do you think they've come from kind of across the lake?
That's a really good question. I think if perhaps we had a longer study period, we could examine this more closely. But in what I was saying earlier, with we were hoping for a storm. We didn't really see like what's normal on a lot of beaches and in a lot of previous years, which is that there's a significant line of beach grass that's been washed back up onto the shore. And we didn't see that in our study. And I guess my theory for that would be that at least the wind direction that we observed was from the north, instead of if it would have been from the west.
We have another question from our online audience. They ask, what would you expect different orientations of wrack to have different effects on zone transport?
Well, as you can see in those pictures, you could see that even the different shape of the woody debris present created different types, different like waves in the shadow dunes that were created. So I would say that it definitely does have an effect. And I mean, I think height plays a lot into that one, whereas a lot of what we saw was woody debris laying on its side. So a lot of it, we didn't see a huge variation in, say, shapes of the woody debris that we found.
Well, we're going to wrap up the questions right now for this team. Let's thank this team for their presentation. They'll be delighted to answer more of your questions after all of the presentations. We'll have the second presenting team come up, and while we're doing this transition, and all sorts of things will be going on up here, the class knows that usually when we have transitions, we do stretches in class. So I'm going to move people in the online audience to stand up and stretch at this point in time. I'll invite people in the in-person audience to stand up and stretch. And if you could maybe imitate some sand moving over some rack while you're stretching, that would be appropriate right now. All right, well, there is always the danger when we do the stretches of actually losing everybody to the stretches. So we are going to continue on with our second presentation. There were a lot of questions after the first presentation related to vegetation. And so the second research team is going to focus on vegetation on a particular type of plant that I think you will find very interesting. Let's welcome this team.
Hello, so our research presentation is on the optimal environment for a regular food plant. I'm Abby Dykstra.
I'm Brandon Price.
I'm Yama. I'm Monica Jones.
The Great Lakes are an ecologically unique region with species and environments that are different than those in other places on Earth, such as the large freshwater dunes. Pitcher's thistle is a threatened species of thistle that is endemic to the Great Lakes dune environments. It is also called Cicerum pitcheri, and both names will be used interchangeably. In order to preserve pitcher's thistle, we can protect its current habitats and create more habitat for it. Our campus has an artificial dune called Perseverance Blowout that is similar to the natural blowouts found on Rosie Mound. Our study will attempt to find what changes would need to be made to Perseverance Blowout to make it habitable for pitcher's thistle.
We have two research questions. The main question is, what's optimal environment for pitcher's thistle? And the other question is, what aspect of Perseverance Blowout may be changed to reflect that? Our objective is to document and compare the characteristics of three blowouts and measure the presence and characteristics of pitcher's thistle and its immediate surroundings in each blowout. And we also will analyze the collected data to identify the optimal conditions for pitcher's thistle to survive.
This was our study area. We chose two blowouts in Rosie Mound Natural Area that were similar in size to Perseverance Dune. Blowout 1, which is right here, had a lot of pitcher's thistle, while blowout 2 had relatively few pitcher's thistle. Our study intended to investigate why pitcher's thistle would grow better on some blowouts and what conditions we would have to replicate on Perseverance Blowout.
Our group used the two methods in this step. First, we used the GPS to locate blowout, and then we measured the change of 6 erosion pins and of each blowout weekly, and to observe their surface erosion organization. And the second, our group did a vegetation survey, and we collected data from the plant health, surface cover, plant density, and the nearest neighbor. And we adopted the random quadrat survey and the quadrat survey by erosion pins. And next, here are the 4 life stages of the pitcher's thistle, and the seeding, juvenile, mature, and the flowering. And in addition, the pitcher's thistle grows for 5 to 8 years before flowering.
This was the map data that we collected while we were out on Rosie Mound. So the lake would be over to the left, and then each blowout is kind of dished this direction towards the lake. These background images are drone images that we collected on the day of our study, so they are relevant in the collection of our data. You'll notice that the pitcher's thistle seems to prefer areas of moderate vegetation and is not growing in areas of complete bare sand or of high vegetation. Also, something to note is that this population over here has a larger quantity of seedlings, whereas this one doesn't, signifying that this population may be growing more than the other one.
So this is the data for the erosion pins that we placed at each site. There's a graph for each dune or blowout area, and then each line is 1 erosion pin that we place at each different section. So as you can see, all of the areas have similar low levels of change within 1.5 centimeters. And we think this is pretty significant because pitcher's thistle prefers low areas of deposition. During our quadrat survey, we recorded the distance to the nearest neighbor to each pitcher's thistle plant. And this is the graph showing the distance. And most of the plants were within 15 centimeters of another one. We also recorded the species during that survey. So the most common was American beach grass. The second was little blue stem, and the third was goldenrod with some other species here and there.
We think that it's significant that American beach grass was the most common because it also prefers low levels of sand movement, along with pitcher thistle. During the quadrat survey, we also recorded the density of the quadrat. So this is not for the Dune area as a whole, but just for the quarter meter square. And we found that pitcher thistle seems to prefer areas of lower density. So what does this mean for our survey? We think that in the context of adding pitcher thistle to Perseverance Dune, the sand movement seems like it would match at Perseverance. But what we think needs to change is the vegetation. So you can see in the pictures of the Rosy Brown natural area blowouts that they are more vegetated as compared to Perseverance Dune on your right. So we think that planting more vegetation with the species that we found during our nearest neighbor survey might help create a more hospitable environment for pitcher thistle. This does raise challenges though, because planting vegetation can decrease sand movement. So we would need to find a balance between the optimal vegetation and still keeping the sand movement.
In conclusion, pitcher thistle seems to prefer areas near Amafo graffiti with low density and high amounts of sand movement. In order to preserve pitcher thistle, we can create artificial dunes that mirror these conditions.
And thank you to Ottawa County Parks for allowing us to carry out our study, and the Michigan Space Grant Consortium, which funded our research. And any question?
So let's start off with a question from Zoom. And it says, why do you think you saw pitcher thistle prefer low density, but also be more likely to be found closer together?
It could be due to just some of the areas that we found during at the blowouts. So some of the areas were 100% density, which is like very covered with dense vegetation, and we didn't find too many pitcher thistles there. The low density areas usually had 1 or 2 plants in the area. They might have just been far away, but that could be a reason.
Sure, I would add that pitcher thistle likes some sand movement, but it seems to not prefer large amounts of sand movement. And so having a neighboring plant close by may help to slow the sand movement down more and create a better environment for it.
Is there currently pitcher thistle found on Perseverance Dune? And if not, where would you source it?
Pitcher thistle is not currently on Perseverance Dune. It's because it's a threatened species, it's highly regulated, and so there'd be special permitting that would be required for Perseverance Dune and pitcher thistle on it.
Can you go back to your plant density graph? Could you just explain that? Yeah, that one.
Sure. So this is demonstrating the density of plants. So when we put the quadrat around pitcher thistle individual, we would look at the number of plants that were in the quadrat, and then the data was like standardized, so we had relatively standard units. And then this was the frequency, like relative frequency. So about 20% of plants were in this 0 density category. And so it's basically showing that pitcher thistle kind of prefers this area of low density. And all of our data was under 40% density, which means that complete cover and even anything above 50% cover was quite unlikely.
So I have another Zoom question that goes right off of this. Could part of the reason for the density distribution be due to locations of past plants that drop seeds?
That's definitely likely. Pitcher thistle grows, as we mentioned, it flowers once every 8 years and then dies, and that's when it spreads its seeds. So a lot of research has been done showing that it tends to be clumped by each other. So that could be a reason for sure.
Are there any other questions?
let's thank this research team. And as we transition to the next team, you could stand up and stretch in your best imitation of a pitcher thistle plant.
That's ours. Right, for this next.
For this next presentation, we're going to rejoin the story, I guess, after understanding wrack on beaches. We're going to head back to the beach environment and the beach dune environment, and we've got a team that's going to tell you about the boundary between the two. Let's welcome this team.
All right, so we are the Sand Transportation via Sand Ramps team. This is our presentation. I'm Austin.
I'm Ryan.
I'm Jake McClure.
All right, let's get into it. All right, so introduction. So from about 2013 to 2019, Hoffmaster State Park saw record levels of Lake Michigan, as you can see with the laser. Post 2020, we start to see these levels go down, leaving behind multiple scarps across the Dune Beach boundary. Our research question looks into, is sand being transported by these sand ramps, and have the scarps evolved enough to allow that sand transportation to happen?
All right, a few definitions you need to know before we dive into our research project is these two that are presented on the screen. First, I'll start with, what is a scarp? A scarp is a feature that's created on the dunes when there's high water levels. The water comes up and erodes a part of the dune, leaving a steep cliff, as you can see here. Second, I'd like to define what is a sand ramp. A sand ramp is a feature on the dune that is created when the wind blows sand sediments inland, and where there's a scarp present, the sand is deposited, and over time, the sand builds up, creating a ramp formation, as you can see.
So some of our objectives were to map the patterns of sand ramps in our specific study area, along with looking at vegetation characteristics in those study areas. And lastly, measuring whether or not sand is getting into the dune system via sand ramps. And our study area was conducted at Hoffmaster State Park between Dune 3 and Dune 2 on the west coast of Michigan. And as you can see, we mapped the coastline and the water as well as the vegetation and the scarps and sand ramps.
All right, for our study, or for our methods, first was the Abney level. We used this to obtain our sand ramp angles. And next we used Trimble GPS units to map out point, line, and area locations such as our ramps and scarps, our vegetation, and our wind station that was pre-established. And speaking of the wind station, here it is. We got measurements from that was established by Professor Van Dyke for a different study. And then we did visual observation of all the vegetation located with our sand ramps and scarps.
The two methods we used to measure sand movement were erosion pins and sand traps. So at each sand ramp or scarp that we chose to study, we placed two erosion pins at the top, and this was And these were used to see whether there was erosion or deposition occurring there. And then we also used 2 sand tramps at each sand ramp. And we placed one at the top to see if the sand was moving over over into the dunes. And then we placed one at the bottom to see the amount of sand that was being moved onto the ramp. Also, another thing I'd like to know about the sand trap is that the opening for the sand trap was facing west, so that the sand that was collected was the sand that was moving from west to east.
So we specifically looked at 2 complete and 2 incomplete sand ramps and found that there's an average slope of 24 degrees. And a complete sand ramp or an incomplete sand ramp is pretty much where the sand ramp is built and it's not quite over the top of the scarp. So sand is not able to get over the scarp quite yet. Whereas a complete sand ramp, sand is able to be pushed over top of the scarp.
Our results for the vegetation. So at the tops, this is where our vegetation was most dense. A great majority of it was American beach grass. The scarps here is a good example. You can see a lot of the exposed roots. And then as we go down the sand ramps towards where our first sand traps were located is where the vegetation got scarce and then very few plots of vegetation along those areas.
The results we obtained from the sand traps showed that there was more sand collected at the sand traps that were placed at the bottom than the ones at the top. And the results that we collected from the erosion pins showed that there wasn't much difference in heights of the erosion pins. The greatest difference was only 2 centimeters, which is probably more because of the surface change rather than actual erosion or deposition occurring. And since wind is the thing that is moving the sand, we thought it'd be important to indicate the wind speeds during our time of our study. So the first box right here in the green is our first week of study, and the blue box is the second week. And these are the average wind speed daily. And as you can see, the first week, the wind speeds were much greater than the average wind speeds during the second week. And we also found that the average wind direction was coming from the south.
So throughout our study, we looked at the scarps and sand ramps and concluded pretty much that not much sand is able to make it into the dune system because the sand ramps have not finished being complete. And we can assume that in the next few years that most of the sand ramps will complete and there will be more sand entering the dune system. And as you can see from the rising lake levels in 2013 to 2019 period, there's left behind scarp. And comparing that to now, currently the scarp has more sand ramps being built and the angles are less. So we can again assume that there will be more sand entering the dune systems.
So as Jake just stated, in conclusion, most of the sand ramps are not completed. There's a pretty even split, but as time goes on, we keep seeing that angle decrease. We expect more sand to be able to move into the dune system as these sand ramps complete from scarps they are now.
We would like to thank our lovely Professor Van Dyke, along with our awesome mentor Luke Atma, and the Michigan State DNR, along with Masters representatives. Questions?
Do you think dune grass helps get sand in there as it can deposit there and stay there? Or do you think it is another obstacle for sand getting into the dune system?
So I think that it can help, at least when it's on top going over, if that makes sense. I think that's what also can help complete those scarps that last a little bit to allow the maximum amount of sand into these systems.
I think if there's vegetation like in front of the sand ramp, then the sand is becoming deposited there and it doesn't really have the chance to go up into the dune system. So that's another way it could hurt it though.
Did you measure how far away the sand ramps were from the shoreline?
Yeah, so we did measure like where the shoreline was currently, and that was that blue line, if you want to. Sorry. Yeah, so right here you can see that's where the shoreline currently was, and like Danny's presentation, the photo is a little outdated, but if you can use your imagination, that is where the shoreline is, and then comparing it to where we measured the scarps with our GPS units, that's the distance. So we don't have an exact number, but
it's in GIS.
Yeah.
All right, let's thank this. We're going to take a break while we transition to our next team. For the in-person audience, if you want to grab another cookie or juice outside in the hallway, we'll give you the time to do that. For a stretch, I see people looking at me like, how am I stretching right now? Well, obviously, sand going up the sand ramp would be the stretch. Everyone gets that. Of course. Oh, of course. Yes, you do. You did it earlier. You do it again. You can do it. You have one slide and then you're done. I'll try you. I don't want to trade with me. Snap your screen. Yeah. No, really. You have to be on Zoom. All right, while we're waiting for our audience to come back to their seats, I'll just make a comment about something that you've been noticing in a couple of the presentations so far, and that's that many of the maps show shorelines that don't reflect the GPS mapping that you're seeing on top of that. I want to assure you that that is not the fault of our researchers. It's not that they are going and trying to grab old maps. Is that what happens in this coastal zone? Change happens so quickly, and so the aerial photographs that are available often are a year or two out of date, and a lot of change can happen in that time. All right, it looks like we have all of our audience back here, and hopefully the people on Zoom have completed their stretching as well. So we're going to go on to another topic now that really focuses on management in the beach and dune environment. And let's welcome this team who will introduce their topic to you.
Hello, everyone. We are the FAME Sand Fence team, and we'd like to welcome you to our presentation on the effectiveness of sand fences on West Michigan beaches. Mesa.
I'm Zachary.
I'm Ashley. I'm Amanda. And I'm
We hope you enjoy and learn from this project that we've worked diligently to present for you today.
So to start off, what are sand fences? As you can see in these images, sand fences are usually composed of thin wooden slats strung together with wire. The purpose of these is to slow down the wind movement, which causes sand deposition behind the fences. For our study, we primarily focus on measuring differences in porosity, evaluating damages, analyzing placement patterns, and observing materials used in these fences in order to see how these factors influence the deposition and movement of sand throughout different locations.
Our study objectives were to analyze the location and configuration of the fences and measure deposition levels in comparison to the porosity and condition of the fences.
Our team worked in 4 different beach locations, each located along the western coast of Michigan. As indicated by the map, 3 of the locations were nearby relative to our home base of Grand Rapids, while one was a considerable distance north. From north to south, the locations were Crosswinds Estates, located in Ludington, a private beach location behind a suburban community. We have North Beach Park, a small public beach in Ottawa County, Grand Haven State Park, a very long stretch of coast with few fences, and Holland State Park, a decent-sized public beach. It should be noted that our study focused on the beach environment instead of the dune environment and its relationship with sand fences, although sand fences are often used for the same purposes in dune environments. The shapes, sizes, and orientations of each location vary quite a bit, which reflects not only in the photos and our mapping, but also in our wind direction measurements.
So one of the main things we had to do is we had to use a GPS to get the maps of the location of the sand fences. To do this, we use Trimble Juno GPSs, and you can see one of us demonstrating that right over there. And we were able to use XGIS to visualize that data. You can see an example map right over there.
So in order to efficiently and easily convey varying levels of damage to different sand fence structures that might be encountered in the field, our team devised a grading system and dubbed it the Sand Fence Status Rating, or SFSR. The scale functions on a 1 to 5 numerical scale, with a score of 1 representing the best condition and a score of 5 representing the worst. The visual correlations are depicted on the slide. As expected, the conditions of the fence structures varied from location to location, but interestingly showed little variation within each. The expected variables as to why this is the case will be discussed a little later in this presentation. So you can see we created just a bit of like a digital representation of what that might look like to simplify it, and then we have as well just in like real life examples of this.
And we also have to measure the deposition, and to do this, we used a variety of methods. One method we used was hand rulers that we used to measure the height of the fences, as that would give us a good idea of how much sand had been deposited at the sand fences. We also used a steady rod and hand level to measure the height of the mound of sand behind it. And a steady rod is the big red stick over there. It has measurements, so you can find out the change in elevation between the person with the hand level and the person with the steady rod. And we were also able to use erosion pins to measure the changing deposition over time, but those were only available to us at Crosswinds.
So because of our different objectives, we were able to collect a wide variety of results. One of our first ones was to look at the characteristics of the sand fences. As Ruth mentioned earlier, they were all made out of thin wooden slats with wire, and some of the ones at Crosswinds also had a netting over them. Porosity is defined as the empty space in a fence that is able to let wind through. We calculated that at about 60% on a fence that was
that we graded as a 1 on our rating scale. And the ones with netting obviously decreased the porosity, but we were unable to calculate exactly what those measurements would be. The erosion pins at Crosswinds Estate also allowed us to compare the difference in how the netting affected deposition. We did notice an increase. I'm doing the wrong slide. Can you flip to the next slide? I'm sorry about that. This graph shows the differences we saw. So the differences weren't as extreme as we expected, but there is a noticeable difference. The fabric covering does a better job of allowing sand deposition behind the fence. We were also able to calculate the average rating that we would give each park. So Crosswinds Estate has the best rating at a 1.1 and Helen State Park at a 2.6. We saw damage at all the parks, as you could see through those numbers. Some of the damage we saw was missing or broken slats, fences that were bowed out eastward, and occasionally fences that were completely missing. Go back. So we were able to map the sand fences and where they were located on the beach. These pictures, as has been said before, are outdated behind the map, so some of the shorelines are not quite accurate in the pictures, but the lines are. On all the beaches, we saw fences that were in parallel rows along the beach. At Grand Haven and Howland State Park, there were 2 rows of fences. At Crosswinds Estates, we saw 3, and some homeowners had added extra. And at North Beach, there was 1 long row of fences across the entire beach, with shorter fences in front of the pavilion and parking lot. The main difference we saw between all the locations was the width between the fences. So that's what this table over here is showing. The smallest width we found was at Crosswinds, the largest width at Grand Haven State Park. So the main result we were looking for was sand deposition, where it was and how much of it there was down of the fences. All the fences we saw had deposition behind them, but we did notice a pattern that is clear in Grand Haven State Park. The west fence has much more deposition than the east fence. We think that this is because as the wind crosses the lake, it picks up more speed, which allows it to pick up more sand, which it deposits behind the first fence before picking up speed again and depositing any extra sand it picks up behind any barriers that are further east of it, or in the parking lots and pavilions of the beach areas. At Howland State Park, the graph looks a little bit different than the other ones. We think there are 2 main reasons for that. The first is that the east fence was put up before the west fence. It was put up about a week earlier. And the second reason is we saw quite a bit of damage to the Howland State Park fences, where there were gaps in the fences or missing fences. Another interesting thing to point out is the difference between North Beach State Park and Howland State Park, which had the biggest difference in when they were put up. When we visited North Beach, the fences had only been up for a week, whereas when we visited Howland, the fences had been up for closer to a month. So it's expected that North Beach would have a much lower amount of deposition than Howland, and that's exactly what we found. We also found that although the fences were stopping deposition, there was sand in places where it was clearly unwanted, like the pavilion at North Beach State Park and the parking lot at Holland. We also saw that Crosswinds Estates had problems with sand creeping into its residents' yards.
Discovered that multiple rows of fences have the greatest effect on deposition levels. Mesh material favored a slightly higher level of deposition, although it wasn't that significant of a difference. Fences closest to the beach have the greatest amount of deposition since the levels are highest there, which was what Ashley was talking about with the western fences. And then finally, fences work better than walls since they don't create problems with erosion.
So why does this matter? Why should a dune manager or a beach manager care? So one of our statistics that you might find interesting is that approximately 33% of the world's population lives within 100 kilometers of the coast. This, this is makes it very prone to changes based on the sand deposition. This demonstrates the importance of keeping some sort of balance with the natural ecosystem of the coastlines, considering how prone dune and beach environments are to rapid change. Sand fences and dunes created by deposition help protect properties. This is important to consider for dune and beach management as it strengthens that aforementioned relationship between man and creation. Some of our acknowledgements, we would especially like to thank the parks and their representatives for allowing us to do our studies, and our mentor, Jess, and Professor Van Dyke. Thank you. Any questions would be answered to the best of our ability.
What do you think is damaging the fences? Is it the wind or animals or people?
All of the above. I mean, it could be anything really. I mean, most of the things you'd see on these types of beaches, especially the public beaches, would be humans, because that's most often what's there. I think if you're reusing fences every year instead of getting new ones, that will over time build up, especially for the wind, it'll build up the damage over time. And also with the private beach like Crosswinds Estate, we also noticed that there was a very low amount of damage, which also can attribute to the fact that there aren't as many people on those beaches. So.
Just to add to that, we saw some fences that had been bowed down by the wind, so that's part of the damages.
We have a question from Zoom. Do you think sand fences could help create complete sand ramps or just dunes in general?
That is hard to say because oftentimes they're not set up for that long amount of time for an actual dune to form, and also they let a decent amount of wind pass through them instead of going over them, so that would be hard to get a great amount of deposition, because it starts to get up and then it starts to go through. We have seen in some cases, like at Holland, there was a decent sized dune forming behind the fences. So if they were left up long enough, I suppose yes, they.
And to add to that, I would also say if you're trying to do it, use the fences to make a foredune or add sand ramps. You'd also need to manually put in plants, because it's the plants that hold the dune together after you take the fence out. And we did not see any plants growing on the amount of sand at any of the pricks behind the fences.
Which also speaks to the fact of how little they're only set up in the times that are where it's not the public beaches aren't being used very much, so they're not set up permanently.
I wonder if your team could speak a little bit more to the mesh that you were seeing over some sand fences. Just explain that, because that seems to be a more recent phenomena in terms of dune management.
Sure. So at Crosswinds Estates, that's the only place where we saw any sort of covering over that. And we saw two different kinds. We saw a mesh covering and a fabric covering. The fabric covering let much less wind through, where the mesh had bigger holes in it. So the point of it is to allow less wind through in hopes of creating more deposition. We weren't able to do too much research on that because of our limited amount of fences with a standard mesh, but as the graph on our on one of our slides that had the graph of the erosion pins at Crosswinds, we did see an increase in deposition behind fences with a fabric covering them.
I think another, I guess, a pro to using mesh on your fences is that it's relatively cheaper and easier to set up than an actual wooden slat sand fence. So it just, cuts the time, but also decreases the porosity, which increases sand deposition.
We have another Zoom question. Did you find the distance between fences affected the amount of sand trapped? And if so, is it more effective to place close together or further apart?
We didn't spend, we weren't able to spend too much time analyzing that, and especially because our fences were all set up at different times, it's hard to isolate one variable as say one causes the other. But there was definitely, I would say that there's definitely a correlation between I don't know what the number is, but a greater width of sand fence deposition.
And I think it's definitely possible to conduct a study on that. That wasn't the main focus of this study, because we had to go to, or we chose to go to 4 different locations in order to get the broadest array of information. So we had to pick and choose of what variables we chose to focus on.
Does the height of the sand fences matter?
All the sand fences we found were really the same height. They were all about 120 centimeters, so I don't know.
Well, let's thank this research team. And before our last team comes up, your next stretch during the transition will be sand fence, trapping sand.
Oh, okay, it's okay. No, it's over.
Okay, well, for our last presentation of the afternoon, I feel like a number of the questions have been leading up to this presentation. So we're going to hear about vegetation again, and hopefully a lot of your questions will be answered. Let's welcome our last research team.
So for this semester, our research team decided to look into how we can predict incipient foraging locations using vegetation.
All right, so for a little bit of background, a foredune is the first visible dune in the system that helps protect larger dune systems from adverse weather conditions. Recently in the Great Lakes, there has been very high water levels leading to the disappearance of the foredune system. But as of recently, lake levels have been receding, leading to barren plains that are optimal for foredune growth. When looking at a foredune, as depicted in Figure 1, first you see embryo dunes, which are dunes that are formed after there are a few shoots in small, tight clusters of vegetation, and then the sand is deposited behind them. These are also known as shadow dunes. And then as more vegetation grows, more sand is deposited, forming incipient dunes. And then as even more vegetation grows, foredunes are well established and get larger.
The research questions that we came to are, what is the effect pioneering species have on the formation of incipient dunes, and how long until there's a stable foredune in that area?
So our study focused on the early indicators of foredune growth. So first we wanted to find out what progress had already been made on the foredune growth. And then we wanted to find out if the plants were actively amassing sand deposits. And thirdly, if the plants were filling in the barren patches on the shoreline. And then we would be able to predict how long it would take for the foredune to mature and where it would mature.
We conducted our study on the western side of Michigan and at Hoffmaster State Park. And as you can see in this picture, we're right along kind of the bare part of the beach where vegetation is beginning to grow. And that creates those shadow dunes that we're talking about. And kind of as you can see in this, Hoffmaster State Park is between the border of Muskegon and Ottawa counties, right along Lake Michigan.
So in order to collect our data and analyze it, we use several methods that includes erosion pins and sand traps. We also use GPS data that we collected in order to find areas and specific points. And we also use pre-existing historical data from the Army Corps of Engineers.
So for our results, over here on the left, we have these little red dots, and this is the GPS coordinates for wherever we saw a clump of vegetation present on the beach. So on the graph on the right, we have on the x-axis the number of vegetation shoots that I estimated per red dot. So for example, you might have a red dot that might only have one shoot, or you might have a red dot that might have 20 shoots, which is quite a lot. And on the y-axis, we have the frequency of these quantities per site, which is Dune 1 and Dune 5. So Dune 5 in orange had a lot of large quantities of shoots per point, as opposed to Dune 1, which had more abundance of smaller shoots, like maybe 3 shoots per clump, but there was 16 points that had 3 shoots per clump. And we also see that Dune 1 totaled to about 62 clumps with about 248 shoots that we estimated, and Dune 5 had around 231 shoots. The average for both these sites was about 3 shoots per clump, as we can see on the graph. And for both sites, around 70% of the vegetation cover was found in clumps of less than 5 shoots. And so in this map, we can also see this white opaque oblong shape. And this is generally the perimeter and area that the vegetation was contained in. So we think that in say 5 or so years, a foredune will form in this area because the vegetation is already in this linear path. And so sand will build up around these points and hopefully form a foredune there.
As mentioned earlier in our methods, we used erosion pins and sand traps to determine deposition and erosion. So during the 2 weeks that we measured that, we found there's really just minimal accumulation. And that's due to a couple of variables. During the kind of the end of the first week, there was quite a bit of rain, and that can have an effect if sand is not moving as much, being wet, it's heavier. And also in week 2, the wind changed direction. Earlier it'd be coming from the west, and then it switched to come from the south. So then that changes the dune orientation from being kind of on the eastern side of the vegetation where it was deposited, changing that to the north since the wind's coming from the south. And since the wind changed direction, as mentioned, that makes it so the sand traps, which were set up to collect sand from the west, we're not getting any sand from the south. And so that just led to minimal accumulation.
So Ammophila breviligulata is the primary species that we found, and its blades slow down the wind, and the blades slow down the wind, and that deposits sand around the base of the root of the shoots. And then the rhizomes form like a lattice under the sand, which kind of holds all the sand together, and that is sort of the foundation for the foredune. We found many young shoots poking up through the sand, so we decided to measure the heights of those shoots as shown in figure 8. And so you can see there's that one shoot, and then there's lots of little baby ones surrounding it. We also wanted to measure the distance these shoots were from their mother plants. Unfortunately, during formatting, this image got turned to the side, but you can see there's like the little shoot and then measuring the distance to the mother plant. So in figure 8, you can see, or the table right there shows the data we found on the shoots from 2 different days. And notably, almost all of the shoots we found were under 15 centimeters. In the next picture, with the mother plant and the new shoots, you can see that these measurements had a wide range of distances, ranging from 30 centimeters to 3 meters. So that's how long like the rhizomes were running under the sand and then hooking up to one of the shoots. And 52% of them were under 1 meter.
With the collected data, we were able to take the amount of established shoots divided by the amount of new roots that we observed. And we were able to determine that there'll be a 13% growth rate within the next growing season, with a possibility of a visible foredune within the next year. With this 13% growth rate, we were able to determine that there will most likely be a well-established foredune in 7 to 8 years' time, barring any major weather events.
So we indeed did see that vegetation was growing and sand was accumulating, even though winter was coming. And the GPS maps show that the vegetation is in a linear line and will probably form a foredune in that area. With the lake level being decreasing in recent years, this trend suggests that right now is the prime growing season for this foredune to start forming. And we think the foredune should increase by approximately 13% for the next growing season and be established in around 7 to 8 years.
So we would like to acknowledge Calvin University and the Geo Department and Professor Van Dyke and our mentor Grace Prom for helping us complete this project and make this study. And then listed here are all of our sources. Are there any questions?
Do you have any reasons or hypotheses of why there was a difference between Dune 1 and Dune 5, where one had a wider variety of number of shoots per clump?
We do not have much data that, well, we didn't have any reason really that those are so different. I forget if one of them is really close to the entrance that you come out onto the beach. It's Dune 5, I believe, which surprisingly that one had a lot more vegetation than Dune 1, which is further down the beach and you have to walk quite a bit to get there. So I'm not exactly sure what that correlation could be. When you're talking about the rhizomes, how did you determine which plant was the mother plant?
So if you kind of like dig your hand into the sand a little bit, you can feel which distance the rhizome is headed. And in the picture that we showed, you can even see like the angle that it's coming out of the ground. So we just measured from that point, following that direction to wherever the closest, like larger clump was.
We have a question from Zoom. Could you clarify what you mean by foredune increase? Is that area, height, or something else?
Essentially all of the above. And I believe about 8 years ago or so, there was what we call a well-established foredune at Hoffmaster. And then as the graph earlier showed, as the lake levels increased, that kind of washed away that foredune. So yeah, as there's more deposition, it increases in height, volume, all of that.
I realize this might not have been part of your scope, but I wondered if you happened to notice whether there was a correlation of the formation of the dunes. Do they, in the same way that we saw the wrack lining up more with the wind patterns than the shoreline, do you see the formation of the dunes lining up more with wind patterns versus shoreline?
I would say yes. Between the first week that we went there and the last week that we went there, we noticed that there was a complete change in the dune behind the plants based off of the wind direction that was happening while we were away.
Well, let's thank our last research team. And I'd like to thank the audience as well for great questions. And any of the team members, please do feel free to ask them more questions about their projects or about their experiences. as you're leaving the room. They'd be happy to talk about that. We appreciate the audience also, the questions that came from the online audience. If you are at Calvin and have extra time in your afternoon, later this afternoon, there is a sustainability showcase at the CFAC, the Calvin Fine Arts Center in the recital hall. And after that showcase, lecture / conversation with with President Reba Bohr, that starts at 3:30, but after that, there's a poster session. And these research teams will be showing posters with their results at that poster session. So that's another opportunity to talk with these researchers. For people who are in the department, there is a seminar tomorrow afternoon as well. So we invite you to look at posters in the department and come back for that at 3 o'clock tomorrow afternoon. And thank you again.